There we go. So hi everyone, welcome to Toronto Data Workshop. This week's guest is very famous in some circles for having written the book on causal inference, The Effect. And if you've not read it, then I highly recommend it. The book is well written, informative, and has very funny footnotes or side notes, as Nick may prefer us to refer to them. Nick is an assistant professor of economics, but don't hold that against him. He's at Seattle University. He's written some fantastic papers, actually. Really worth going and checking out his website. One personal favorite of mine, and I promise I'll get to I'll allow our guest to speak in just one moment, but one personal favorite is he got a bunch of students and he had them replicate the data cleaning and preparation work that underpins some data science projects. And he basically found that the difference in the results, in the subsequent results, is much larger than their confidence intervals. So essentially, we're really just creating our own results to a large extent in the social sciences. And so thank you very much for joining us, Nick. Really looking forward to your presentation.
Well, thank you. All right, let me go ahead and share my screen and we will get going. So, all right, so, oops. So one clarification. So most of these are not students. These are largely professors doing the replications with a couple of student assistants. I think, let's see here. Nabin Chen was a student at the time. Godwin Ekpe was, and Jeffrey Blom was at the time. He was almost finished, and now he's a professor. Okay, so the idea here is this, right? When we are doing a study, if you've ever worked with data, as I'm sure all of you have, you know that there's hundreds of decisions going on in every single study, right? And we focus a lot on these sorts of decisions when we're talking about analysis a lot, right? That discussion happens. You always worry about when you present a paper, okay, somebody's going to raise their hand and they're going to talk about my errors. Somebody's going to raise their hand, they're going to talk about the model that I'm using. Somebody's going to raise their hand, they're going to talk about, et cetera, right? But there's a lot else going on as well, right? Data cleaning, how you clean the data and prepare it, the way that you select your sample, and then also even stuff like which software commands to use. Like when you run a regression, what language you're using, what package you're using. And I can tell you, having written a textbook where I do all the code in 3 different languages, they don't line up a lot. There's a lot of differences between them. It's very, very common for the exact same analysis to actually be different analyses in different languages just based on the defaults that they choose, or sometimes maybe errors in the code. And in all of these cases, in some cases there's a wrong answer, right? In some cases there's a mistake that's been made. The analysis could be better, and that's definitely something that goes on in research. But also sometimes there's just multiple right ways to do the same thing. And I refer to this, and this is not my term, but this is a researcher degrees of freedom is the way that you can think about it. That in any given study, there's a lot of different ways you could do the same thing, and which way you choose to do is going to affect your results. And this is going to be, even though all those options could be correct, right? They could all be totally justifiable reasons, which is actually a bit more sinister, right? Because if it was obviously wrong, somebody could look at it and say, oh, this is wrong, I shall fix this problem in a replication or whatever. But if somebody looks at it and says, yeah, that's a reasonable choice, I'm not sure I would have made it the same way, but that's reasonable, they're not going to check you, right? They're not going to go in and like, oh, I'm going to try a different reasonable approach. Or, if they did change it and they found that it completely messes with the results, who's going to publish that replication, right? Getting replications published is hard enough already. And now try to get a replication published when you're not even saying there's anything wrong with the original paper. You just did something different and you got a different result, right? Good luck with that. And so a lot of these choices are also invisible to reviewers, right? There's a lot more decisions in the code than can ever possibly be in the paper. And so the question is, does this stuff matter, right? And if these invisible and seemingly unimportant choices really are important, if they really do matter, then there's there's some problems there that we're going to have. So what we do in this paper, we use a many analysts approach, which is where we have the same study being replicated multiple times blind by different people. So the idea here is that you have one study, the identity of that study is kept secret, the original results of that study are kept secret, and then everybody is just replicating that same study based on a certain set of assumptions, the same data being used, all that sort of stuff. What we find is that there's large and apparently invisible differences in data cleaning. that one thing that is being left out of many analyst studies is that they are not really allowing for that research degree freedom in the data cleaning stage, but there does appear to be a whole lot going on there. There's also meaningful differences in analysis, although those are easier to catch because we are more attuned to looking for those. And what I find is that the between researcher standard deviation in the results is about 3 to 4 times the reported standard error. So if you're reporting a standard error of 0.02, then if you got a bunch of different people to replicate that exact same study without knowing what you did, you might end up with a standard deviation across the replications. It's about 0.08. So that is concerning in a lot of ways. So first of all, what is a research degree of freedom? It's anytime you could make a choice one way or another, that is a degree of freedom, right? And to be clear, this is not quite the same as mistakes. Here I'm citing a famous economics example, which is Reinhardt and Rogoff, which you might have heard of. They were the ones who said that your debt to GDP ratio is really bad once it gets up to, I think, 80%, 90%. And then it turned out they just had an Excel error in their code. It's not quite the same as p-hacking, right? Because we're not necessarily saying that people are trying to get certain results or significance of the results. There's different right ways to do the same thing. It's also subtly different from the garden of forking paths, if you're familiar with that. Because again, we have the exact same analysis we're aiming for here. It's just, there's some choices that must be made. All right. So we give researchers control over data cleaning, model selection, control creation. But what we are keeping constant is that everybody knows, is that on the next slide? No. What everybody knows is what they're trying to estimate. And what the data is. So we gave everybody the same data. We say, here's the data set that you're supposed to use. It's not cleaned yet, but here it is. And here's the estimate that you're trying to estimate. And here are the assumptions that you're going to make. So to give a very basic example of what this could look like, let's imagine that I gave you some experimental data and I said, assume that variance in both these groups was going to be equal beforehand, right? That's the sort of, or assume that the randomization was done properly. Those are the sorts of assumptions that I'm talking about. So as we go through, I then coded up all the code, right? I went through everybody's code line by line and reported exactly what it is that they were doing, excluding or including the exact kind of choices they were making, and then whether this would likely be reported in a write-up or would be sort of ignored and kept in the replication code. Now, this is not the only many analyst study. There were 2 main ones that came before, one on fMRI analysis by Botvinnik-Nezer and a bazillion other authors. All these papers have a bazillion authors on them because the sort of standard is you give co-authorship to anybody who does a replication, which I think is pretty good as a standard. There's another one on discrimination and soccer penalties. This is the one that sort of inspired everybody else to do theirs. So you see a lot more coming out recently, and they all sort of cite this one as the original. In both these cases, and then another one, which is not even in academia, predates all of this, was on 538. They gave the same pollster data to a bunch of different polling houses to see how they would adjust it. And they, this was in the 2016 election. And all 3 of these, and pretty much all of the studies, many analyst studies that I've seen, find considerable differences across the analyses when you look at different results. The extent of it varies. Some of them find, it's just that certain hypotheses that they test are more consistently agreed upon than others. Some of them find that the variance in the results is quite large. Some of them find that the results jump and switch sign from thing to thing. But all of these really focus on differences in analysis. They provide a cleaned data set to the researchers, who then decide how to analyze that data. Also, some of the more recent work asks why these differences occur and sort of what tamps them down. So an obvious question is, how about peer review, right? So, you do these many analyses, you run it through peer review, which is not something that we do, which would have been nice. It just wasn't really feasible in our case. And you do find that peer review reduces the amount of variance between different studies, right? That it sort of brings you to more similar, at least, results. I don't think I've seen anything about whether it led to less variation in the actual choices, but at least less variation of results. So there's that. There's a paper that just came out in Finance that also found that peer reviewed helped. They coined the term non-standard errors for this sort of thing. I'm not sure that I like that term, but you'll probably hear it in the future. It is very catchy. There's another cool paper by Osberg and Brudel, which reanalyzes the Silberberg and Zahn, or not Silberberg, Silber-Zahn paper and finds that a lot of the variation was due to an imprecise research question. That the question that they had in that study was, is there discrimination in the provision of penalty cards in soccer, racial discrimination? And that was that question was interpreted in multiple different ways by the multiple different teams. And that once you accounted for the differences in question interpretation, that really tamped down. So there's two different ways that are sort of emerging about what might help reduce this in the future, at least on the analysis side. That peer review helps, and we already have that. So, great, assuming that the peer review works in a similar way to the way that it does in these experimental studies, which that I'm not sure about. But also that clarity of research questions, which in the social sciences could definitely be a lot clearer, would also help. And is something that maybe we need to work on. So in this actual study, we have two different studies in applied microeconomics. And in each case, we recruit a set of researchers to replicate each of these studies. All they know is the raw data set, the identifying assumptions that you would need to justify a certain kind of causal design or causal inference design, and the research question itself. Everything else is degree of freedom. Literally everything else, you are basically trying to produce the result that you would put into your abstract answering this research question of interest. We decided to include data cleaning in this because we're economists. Most of the data that we work with is administrative in nature. It's not experimental. And we are always having to clean our data. And so we naturally ask the question, how much does that matter? So in terms of selecting the studies, let me check on my time here. I should just have my phone out for that. We wanted studies that were well regarded. So if we got weird results, it's not just, oh, you picked bad studies, but we didn't want them to be super famous because we didn't want the replicators to recognize the study and know what the original results were. We wanted them to have publicly available data and with a research design that could be clearly explained to replicators, right? So if you're doing something, wild with a 18-part structural model, great, but there's no way that I can tell the replicators how to replicate that without just telling them what to do, which is not what I want. So we ended up on two. One is Black, Deborah, and Salvanis, which is looks at the effect of compulsory schooling on teenage pregnancy. Uses state-by-decade variation in compulsory schooling laws from census data. So basically, if you are forced to stay in high school through 16 before you're allowed to drop out, does that reduce your probability of having a teenage pregnancy? They do a bunch of other stuff in the paper. We focus on just one of their estimates, which is, does changing the compulsory schooling age from 15 to 16 reduce the rate of teenage pregnancy? The other one we do is Fairley, Kapur, and Gates. This is looking at the effect of health insurance on entrepreneurship. So in the United States, when you turn 65, you become eligible for Medicare, which basically makes healthcare much cheaper for you. And it also makes healthcare not tied to your employment. And so the question is, when you have the opportunity, do you then quit your job? Because you don't need your job for health insurance anymore. You can now start your own business. And so it uses the current population survey for a small time series rolling panel. You observe the same people 4 months in a row. And so we're basically picking out the people for whom they turn 65 in the middle of those months, and then asking if the business formation rate among those, it's the self-employment rate among those jumps after the 65 barrier. This is sort of like a regression discontinuity, but with a very short running variable. So recruiting for the replications, we emailed the department chair of every major US econ department, which roughly you can think of as basically anybody who has a PhD program, and asked them to pass recruitment on. We also posted on Twitter. The link was clicked 638 times. The intent was that we were looking for replicators who were sort of representative of people who publish work. And they should be producing work in the exact same way that they normally would. If they use assistants, that sort of thing. We got 49 people to sign up. 49 qualified people to sign up. There were some people who were sort of too outside of what the requirements were. Of those, 12 finished the task. People who did not finish largely cited time issues, and there were no real observable differences to people who did finish and didn't finish. So there's selection into the volunteer group, obviously, but there's not really a whole lot of selection into the finishing the task group, at least not on observables. All right, so getting to the results, basically, right? So the first one that we look at here is the teen pregnancy study. So this is the estimate and the confidence interval. So we asked everybody to produce just one estimate and confidence interval. So typically in an economics, applied economics paper, you'd have a lot of like robustness checks and alternative model specifications, things like that. But I said, you can do all those things, but I want you to give me the result that you would put in the abstract. The idea here is that we could get a huge range of results for everybody, but that wouldn't really tell us as much about what's really going on different. So another degree of freedom here is which of the many analyses that you run is the right analysis as well. So here we get a huge difference, right? There's lots of differences across different studies. So this is the effect of the additional year, raising the compulsory schooling rate or compulsory schooling age can be anywhere from a positive or negative effect on teenage pregnancy rates, reducing them by 2 percentage points, all the way to a positive effect of 2 percentage points. So the sign flips, the significance changes as you go along, lots of differences in there. So not looking great for that. In terms of what was actually different, there were, if you have a big table, you might as well just show it in the paper. Sorry, it's this one. Oh no, where did it go? There it is. So these are the differences that were actually made, the differences in choices. And I'll spend a little bit more time on this as if we run out of time, I'll skip the second study. You sort of get the idea from looking at one of these. So in terms of what they did differently, everyone picked the same data set. I told them to do. It'd be really weird if they used a different one. Everyone limited the data to adult women subjects, and so we had instructions here on what you were supposed to do in order to keep things, roughly comparable. And so everything with a star here, we told them to do. So limit the data to women who are age 20 to 30. One person did not do that. They said that they thought that it was more appropriate to go broader. Drop women with first birth age 14 or below. One person just, I guess, didn't see that part of the instructions. Another person defined it differently. So they used, instead of greater than or equal to on 14, they used greater than, and that led to it being age 13 or below. And then this person, that was the difference, right? Yeah, this person did see that part of the instructions. They coded them as not teenage births. So if you had a birth coded in the data at age 5 or whatever, like obviously that's a mistake. They coded that person as having given birth, but not not as a teenager, as opposed to dropping them. So assuming that the problem there was their age, not that the problem was that they had a birth, right? So one of those things is wrong. Which one? We had 2 states that did not have any policy information in them at all. Everybody dropped those, right? One person dropped everybody who's living in group quarters, which is a common cleaning thing that you would do in this data, but nobody else did it. One person dropped. There's 2 different 1970 samples in the data. One person dropped other ones. Somebody dropped women who'd never had children, so it was just comparing people who did have children, but did they have them as teenagers or not? Then this person limited it further just to household heads. And like, none of these are bad decisions, right? It's just that nobody else made them, right? If the X's were across the board here, then that would be more reassuring, right? So it's not that this person made a mistake. It's not even that everybody else made a mistake. It's that it's inconsistent. And then there were also differences in the definition of variables. So one interesting thing that popped up, and this was sort of so in the original paper that we got the policy information from. So this is looking at what is the compulsory schooling age policy in different states at different times. And they have a table in the back of the paper with those policies, and that was what we passed along to the replicators. On that table, there is what very much looks like a typo, that Ohio is ranked as having a 18-year-old minimum schooling age in almost every year, except for one where it's listed as 8. So is that a typo? They just left off the 1 from 18, or is that actually a change? And so one person changed it. Everybody else left it. Although granted, 2 of those people said, I thought I should have changed it. If I was really doing this on my own, I would have changed it, but I thought you wanted me to be consistent. So there's maybe a little bit of ambiguity there as to whether that is a problem. There was one paper that matched, we told them how to line up the policy years to the people. One person did it slightly differently. And then finally, there's the question of, does somebody who has a birth at age 18, did they give birth by age 18? So that one person differed on A big thing here, if you look down, is that sample sizes differ quite a bit. There's actually no two researchers who report the same sample size. It differs quite a lot. The big one here is because they didn't drop women outside the age range of 20 to 30. But even within that, like even the ones that are pretty close, like, and I can tell you for the ones that are really close, I couldn't really figure out why they were different, even reading through their code very carefully. So the replication code wouldn't solve this problem. You know, so is it 1664000 or is it 1669000? You know, what's the right answer? There's not really a right answer, but there's some differences being made here. In terms of the point estimates being different, right? You can see this is just the results from that graph. And then we also tried to re-estimate the models. Use the different data sets but the same model. So there's differences in both the data set and model encoded in this row. But what if we just make it the differences in the data set? So we fix everybody to use the exact same model, but then estimate that model on the different data sets. It tamps down on the differences a bit, but we still get that it goes from negative to positive. So it's in this case, it is mostly the data cleaning decisions that lead to the differences. Sorry. There we go. There's also differences in the analysis, which again, I will pop up here. So these are differences so in this case, pretty much everybody used the same sort of design. So it's a pretty, I mean, once an economist hears the term state-by-state variation over time, everyone thinks the same thing, which is basically a two-way fixed effects model. At least they used to at the time when we were doing these replications. These days, there's been a bit of change in that. So everyone used basically the same structure, but there were also differences in terms of the analysis that was used. So everyone used state fixed effects across the board. Everyone used some sort of control for cohort in some way. Some people did birth year fixed effects. Some people did year fixed effects, which in this data would have a similar kind of effect. Some people did year by age. Some people did age fixed effects, which again would have similar effects to the birth year. Some people did year by age fixed effects, so a two-way fixed effect specification. Some people controlled for race. Some people did not. Some people included time trends. Some people did not. Some people controlled whether the spouse was the household head. Depending on your field, you'll either find this very funny about economists, but about half of us used sample weights from the data, which were provided in the survey data, right? The survey sample weights. Economists get a bad rep for not using these, apparently well-deserved. So here's the estimates, the same ones from before. And then we did the opposite thing. So the first table showed what if we fix the model, everyone uses the same model, but we use different data sets, how different are the results? Now this one is what if everybody uses the same data, but uses the different model that they chose? And this tamps down on the results a lot more. So in this particular instance, and also it turns out in the other study, which I don't think I'm gonna have time to go over, yeah, probably not, it was mostly the data differences that were driving the differences between the studies. So by the time the data was prepared and it came time to choose the analysis, most of the variation was already sort of accounted for by there. Not all of it. We still get one positive result among the negatives, and significance certainly varies across these rows or these columns. But in this case, most of it was data cleaning as the differences. All right. Health insurance, I'm not going to go over all the details. It was a lot better behaved in terms of the results, although interestingly, a lot more differences in terms of some of the data cleaning. So everyone gets a positive result, great. One person gets a weirdly high result. The significance varies across different variations. So, all right. So to sort of summarize what we have, in both studies, there were major differences in data cleaning. No two studies in either replication had the same sample size. I don't show that here, which is a bit concerning, right? And even in the, that's worrying, right? Especially because I could not, in all cases, figure out why the sample size was different. Even though I had full access to the replication files for everybody, even though I walked through them line by line, even though I was taking notes as to all the exact decisions that they made, I still was not able to completely pin down why all the differences were there. So in some cases I could, but in some cases I couldn't. Big differences in the construction of selection and selection of controls, which is not surprising. We always argue about which controls should be included and which controls should not be included. But also differences in construction as well. In the second study, there were different, when I mentioned that it was sort of a regression discontinuity kind of setup, there was a lot of variation in, how many polynomial terms do we have on the left and right side, and that affected the results a bit. Do we include controls? Some people like to include controls in regression discontinuity design. Some people do not. So there was differences there. And a lot of these differences would be unlikely to be reported in some sort of write-up, especially on the data cleaning side, right? We all talk about how we prepare our data in our reports, but there's no way, it's just impossible to include everything. We do have analytic differences that we would talk about. Those are more standard. We tend to be on the lookout for those. In terms of how this plays out in the actual results, it happened to be that one of the studies was majorly affected and the other one was more minorly affected. But it's also not super obvious why that is. Like if I was looking only at the differences in the data cleaning choices, I would have expected the second study to be more varied because there were much bigger differences in terms of the actual sample sizes that they ended up with. But it could be that the analyses that they chose controlled it all away. I don't know. So to conclude, there's lots of choices that we make as researchers that don't necessarily have a right answer. So could go either way. Don't get written up, but do matter anyway, right? This is pernicious because even if we already don't enough go through each other's code and try to see what's going on in it and check for mistakes, right? But even if you did go through the replication code of a published paper line by line, you might not spot any problems that would make you want to try something different because they didn't have any necessarily problems. They just made a choice in a different way, right? We are not so well set up to check this stuff. A replication study would not really get at this because when you're doing a replication, you would want to keep constant all the choices that you don't think would necessarily matter, right? Peer review wouldn't necessarily check this. I mean, those other studies seem to suggest that peer review sort of shrinks the error, but there are also a lot of choices in here that peer review would not catch. Data availability and cleaning code from raw data would help. So more standardized provision of data sources that has done a lot of the data cleaning steps for you would at least have everybody making those choices in the same way. So for example, there's a paper by Nolte et al. In 2010 that sort of takes these many analyst studies, including ours. One of the cool things about presenting a published paper is you can see what has cited it. And they go through a standard real estate data set and they provide a set of standardized data cleaning procedures that you can use. And that would help tamp down this issue in the use of that standard data cleaning set. More preprocessed files, IPUMs, for example, is a great source of preprocessed data. We used IPUMs in this data set, and so there's still more data cleaning choices to do from there. But also, if we had used the raw CPS files, there would have been a lot more choices to make and a lot more mistakes to be made as well. So the presence of IPUMs probably makes this less varied than it would be otherwise. But also just in general, when you are reading a study, if the standard deviation across replications would be 3 to 4 times the purported standard error, there's a lot of variation that we're missing in our understanding of results. And I missed this one, but on the analysis, there's a lot of solutions to this on the analysis side, things like model averaging, for example, but these would not get at differences in data cleaning. All right, that's it. Thank you.
Thank you very much, Nick. Obviously incredible paper, incredibly important, and obviously well ignored by the profession. So I'll get to some questions. If folks have questions, they can just raise their hand and I'll call on them. I'll just record our first question, and after that, the questions period isn't recorded. But our first question is always, do you have any books that you'd recommend? And obviously, you should include your own.
I'll include my own, The Effect, which is about causal inference. There have been a lot of great books sort of along those lines. I mean, so Scott Cunningham's Causal Inference Mixtape is great. Regression and Other Stories by Gelman is also fantastic. I'm still looking for one that sort of addresses the data cleaning side of this, because it's a hard subject to write a book about, right? Not a whole lot of that. Sort of outside of those lines, I think a book that I recommend a lot because I think it's just fantastic is The Measure of Reality by Crosby. And this is about sort of the development of the idea of quantification in sort of Middle Ages to sort of a little bit afterwards, right, the Renaissance era Europe. And we are all data people. We measure everything. That's what we do, and that is a relatively novel concept. And thinking about the difference between a world where measuring stuff is just not as important, and I think sheds a lot of light on what data actually is and how we can use it. And that paper I think is really great, or that book is I think really great. It's a fun read too. So there's that.
Oh, thanks very much, Nick. So I'll just stop recording.